Welcome to the first lecture in Intro to Astronomy. In this first lecture, we're going to discuss the units, sizes, and distance scales of the planets, stars, and the galaxies that you will need to comprehend the material in this course. We'll introduce some mathematics first of all. Not a lot, but just enough so that we don't have a lot of zeros on our screen constantly. The distances to the planets and the stars are extremely large, so if we are to quote such things in meters, miles, or kilometers, we'll need a lot of zeros, and scientific notation, as it's called, is a method of reducing the number of zeros that you have to actually read and count. So we'll discuss that. Then we'll move on to the units, the typical units that we talk about in terms of size, distance, and time in astronomy, and then look at the scale of the planets, solar system, and galaxies themselves. Now, when we talk about units in science, especially modern science, we're really talking about using meters as length, or quite often in this class, the kilometer, which is thousands of meters, masses in kilograms, which will be very important later when we talk about force and we talk about gravity, and time in seconds. Well, not always seconds, sometimes years and sometimes in months, of course. But before we do that, let's take a look at some of these numbers here, these conversions. There are many ways to express a number. One of them, here we're looking at a meter, a length here. One of them is to say, well, if it's a very small length, it could be 0.000001 meters here. This could also be turned into 1 times 10 to the minus 6 meters. This is still the same measurement, it just means this 1 has 6 decimal places before it. This is a lot more concise to read and to write than this, and causes a lot less confusion. This 10 to the negative 6 here can also be replaced by a unit in its own right. And this little prefix, this mu in Greek here, is the micro or the micron. So this is 1 micron, 1 micrometer, 1 times 10 to the minus 6 meters, or 0.000001 meters. This method can also work the other way as well. Here we're looking at 1,000 grams. This, of course, could be 1 times 10 to the 3 grams, 1 with 3 zeros after it. This would also be equal to 1 kilogram. We can also look at time. Time is a little bit more complex, but in terms of time, we're looking at one day being 86,400 seconds. This is 1,440 minutes, or 24 hours. Of course, we will then have 365 days in a normal year, each one of those comprised of 24 hours. So when we look at these units, we can say here, if we want to convert them, as in civil terms, we still see a lot of measurements in feet and pounds, which personally I could do without, but that's what we have. So if you want to make sure you're on the right page sometimes, and that you're really understanding these lengths, and it's a little more intuitive, 1 meter is about 3 feet, 1 kilogram is about 2.2 pounds. Time, whether it be in SI or in units of feet, pounds, is still the same unit. It's invariant. So distances on, say, a planet's surface, distances to the next town, can often be measured in kilometers, but if you want to convert them and think about them and how long it would take you to drive, quite often kilometers are not the most informative unit. I will not convert things to miles as a matter of course, but 1 mile is about 1.6 kilometers, so roughly double if you're watching these lectures and thinking about these measurements. Now when we talk about time, time is the same unit in both the US and the SI system of measurement. And it's really based on the orbital period of the Earth. So the Earth goes around the Sun, completing 1 revolution, that's 1 year. It spins on its axis once, that's 24 hours. That's our day length. So these particular measurements of time are invariant between the two methods of units. So time is the same in both US and SI. 1 year, 365 and a quarter days, 52 weeks, 8,766 hours, 525,960 minutes, 315,500 seconds, as you can see. So, if we can do these conversions, this is the kind of things you would see from, say, astronomical formulae. Not that we're going to be doing a lot of calculation, but when we are looking at these values, as we'll see later on, things like the length of the year will actually change with time, over very long time periods, granted, but they will change. So scientific notation will become very important. So you're not saying blur, as I did in the previous slide when you're looking at a long number. So we'll see in this class very large and sometimes very small numbers, and we will have to be pretty well practiced in understanding what 10 to the 6 and 10 to the negative 6 means. There's no real calculations to do here, but when you do glance at these numbers, do have an idea of what they mean. If you have a scientific calculator handy, you can always punch all these numbers in, all these zeros, and hit the ENG button, and it'll actually translate it to this method for you, this method of notation. Or, likewise, if it's 10 to the 6, you can hit this ENG button, and you can see the complete number of zeros. So while we won't do any calculations per se, you might want to do that for yourself occasionally as you're looking through the material. So just as a quick guide, if you were to see 10 to the 2, for instance, this would be 10 times 10, which would be 100. So 100. 10 to the 3, 10 by 10 by 10, which is essentially 1,000. The opposite way, 10 to the negative 2, would give you 100th. So this would be the centimetre scale. And here are some of the common prefixes. Here we can see the very small measurements and the very large. Later on, we will discuss things like radio telescopes, microwave and gamma rays, and the energy of various wavelengths of light, which may refer to nano and micrometers a little bit. But for the first few classes, we're going to be dealing with large objects, planets, solar systems, galaxies, and galaxy clusters. So, for the first few classes, we will be focusing on the very large, which would be kilo being 1,000, mega being basically a million, and giga being in the billions range of 10 to the 9. So for this class today, we'll use these very large numbers. So let's take a look at the scale of the universe. Over here, this is basically the Earth. This is the planet that we live on, as imaged here by the Apollo 17 spacecraft. If we're to measure distances upon the Earth, we would probably use a unit such as the kilometre. The Earth is part of the solar system. When we're looking at the solar system, we could use kilometres, but there are other units, such as the astronomical unit, which is the distance from the Sun to the Earth, and we'll specify that a little more as we go. But the Earth is part of the solar system. The solar system, the Sun and all of its planets that orbit the Sun, fit into the Milky Way galaxy. Our star is but one of many, many thousands in the Milky Way galaxy. So there we are in the spiral arm along the bottom of the Milky Way galaxy. And of course this galaxy is also rotating, so our position is constantly shifting as this galaxy turns. Our Milky Way galaxy that our star resides in is actually part of what we call the local group. And this is a group of galaxies in the local region of space, with galaxies such as the Andromeda Galaxy being members of this local group. Now, the local group itself is a member of an even bigger group of galaxies that we call the local supercluster. And the local supercluster is a cluster of groups of galaxies. So that's our distance scale. Here we are on the planetary scale. The planet is part of the solar system, which is part of the Milky Way galaxy, which fits into the local group, which fits into the local supercluster. So we're going from relatively small scales in planetary terms all the way up to galactic and intergalactic scales for clusters and groups of galaxies. So in terms of distance units in astronomy, the distances we really want to define are very, very large. If we're to talk about the distance from the Earth to the Sun, we're literally talking about 150 billion meters. That's a lot of zeros to keep writing, especially if you are doing a calculation as a scientist. And to keep track of them, we'll use the scientific notation here. So one astronomical unit is defined as the distance from the Earth to the Sun. So one astronomical unit, or abbreviated as AU, is about 150 billion meters, or 149.6 times 10 to the 9 meters. Now the Earth's orbit isn't perfectly circular, so there's a little bit of variation in this distance, so this is a bit of an average. As we step up our distances and start to talk about distances to, say, the nearest star, the astronomical unit actually becomes inadequate, and we start having far too many zeros attached to our astronomical units. So we move up and we use the light year. Now the light year, even though it has the word year in it, is not a measurement of time. It's a measurement of distance. It's how far light travels in a single year. So if you could move at the speed of light and keep moving at the speed of light, by the end of a single year, you will have traveled 9.46 times 10 to the 15 meters. Quite often, when you're looking at astronomy, especially when you're looking at the distance to faraway stars and galaxies, there's a method that uses something called parallax to determine those distances. So the distance to a star with what's referred to as a parallax of 1 arcsecond is given by the parsec. Now we'll define parallax and discuss this a little later on, but right now you need to know that there's another unit which is comprised of light years. So on about the same distance scale, we can have light years, or you can often see a value quoted in parsecs. And 1 parsec is 3.26 light years, or 3.08 times 10 to the 16 meters. It is not necessarily a measure of time as quoted by Han Solo in the Star Wars movies. This is the parsec. It's about comparable to the light year. So when we are looking at planets, and as the slide shows, the planets I'm about to show are not shown to scale with one another just yet. When we're talking about planets, if we're to measure, say, the radius of a planet, it would be quite acceptable to use kilometers. To use the light year here would be foolish, and to use the centimeter would be a little bit small. You end up with very big units here, very big numbers. So think about where would you use these specific units. If we're defining a distance between 2 points on the Earth, or the radius of the Earth, then we would rely on kilometers. And quoting about 6,000 kilometers is not incredibly unrealistic. By comparison, if we're to look at a small planet such as Mercury, the closest planet to the Sun, then its radius is about 2,000 kilometers, 2,440. You don't have to memorize these values. I just want you to understand the various sizes of the planets in the solar system. So here, kilometers are once again a reasonable unit to use. If we're to look at the gas giant planets, such as Jupiter, the biggest planet in our solar system, then we can still use kilometers. But now we're talking about 69,911 kilometers for the radius of Jupiter. Remember, the Earth was about 6,000 kilometers, so this is a much bigger planet than the Earth. And again, these planets were not shown to scale. Now they're shown to scale. So you can see here the closest planet to the Sun, Mercury, the nearest gas giant of Jupiter, and the Earth, all in comparable scale to one another. And the kilometre here would be a relatively reasonable unit to use. So that's the kind of sizes you could expect to see of the individual planets themselves. What about the distances to each of the planets? Here's one of those typical pictures you see, the kind of thing you see on a child's bedroom wall, where all the planets are nicely lined up. We have Mercury here, Venus, Earth, Mars. Here we have an asteroid belt, which is a little bit misleading. These essentially large rocks left over from the formation of the solar system are actually quite difficult to find and are very, very spaced out. This, again, is not like a Star Wars movie where it's very difficult to maneuver between them. There's very big distances between them. We then have Jupiter, largest of the gas giants, Saturn, Uranus, Neptune, and, as I'll discuss later, still including cold and tiny little Pluto all the way out on the edge of the solar system. There are myriads, comets, and other floating bits of rock which will come through the sky and intersect with planetary orbits occasionally and interact with them and appear spectacularly in the sky. Remember, the planets are not nicely lined out like this. They're not all in one great big line. If you were to leave on a rocket from Mercury, you wouldn't just be able to fly to Venus. Venus could be on the other side of the Sun, for instance, to Mercury. And they're all spaced out quite large distances. So this is the kind of thing I mean. So here we have the Earth, Venus is on this side of the Sun, Mercury's here, Jupiter's over here. So the planets are not all in one nice neat row sitting there for you to visit. And as I said, using astronomical units can actually be very convenient. So if we're actually looking at the size of the solar system, this is the size of the solar system, 11,830,000 kilometers. And to avoid having to say 0 kilometers, we can use the astronomical unit. Remember, the astronomical unit is the distance, or average distance I should say, from the Sun to the Earth. And as you can see with the orbits of the planets plotted here, most of them are relatively well behaved. Most of them are in relatively the same plane. Things like Pluto come up out of the solar system and then down below it. This is one of the reasons it was kicked out of the Planet Club by the International Astronomical Union. We also have comets, which tend to have very erratic orbits. They will come up out of the plane of the solar system as per something like Pluto, but also they will cross the orbits of many different planets. So remember, when we are looking at the size scale of the solar system, the astronomical unit is very useful. And here's that definition. So, as I said, the astronomical unit is really the average distance from the Sun to the Earth. The Earth really has a slightly elliptical orbit, but for our purposes, we've taken an average and we've actually assumed the Earth's orbit is pretty circular, which is quite true in a lot of ways. But that distance is then one astronomical unit. And this is a lot nicer to quote than all of those various kilometers. So if we look at the distance to the planets in astronomical units and their equivalent in meters right here, we can actually end up with this very nice unit. So here's Earth sitting at 1 AU. There are two planets inside the orbit of Earth in smaller orbits. Mercury at 0.39 AU, very close to the Sun. Venus, 0.7 astronomical units. Earth at 1, here we are at 150 million kilometers. We then have Mars, that's out at 1.5 AU, so 1.5 times Earth's orbit. Then there's a big gap. We do of course have asteroids floating around in here, but there's a big gap, and we have Jupiter at 5 astronomical units. We're now looking at thousands here of millions of kilometers, 7,783 million kilometers. The next planet is Saturn at nearly 10 astronomical units, Uranus at 19, even further out. We'll talk about the discovery of these planets and the difficulty in finding them when they're so far from the Sun. Further out, Neptune, 30 astronomical units, and then Pluto, right out on the edge at nearly 40 AU, or about nearly 6,000 times 10 to the 6 kilometers. Another convenient way of looking at distances within the solar system, rather than actually quoting astronomical units and meters, is to look at things in terms of light travel time. And this can be very useful if we're sending probes, if we're sending spacecraft to these various planets, because those spacecraft communicate using radio frequency transmissions, and radio waves propagate at the speed of light. So, if we were to send a probe to, say, Mercury, then we will have a light travel time, and we'll have a delay in the signal leaving the Earth and being received by that probe. The light travel time that we're actually showing here is how long it takes light to go from the Sun to that planet. So if you were to switch the Sun off somehow and just make it go completely black, it would take 3.2 minutes for you standing on Mercury to realize that the Sun had gone off. So light leaves the Sun and takes 3 minutes or so to reach Mercury, or 0.39 AU, to cross 0.39 AU. Venus, 6 minutes. Earth, nearly 9 minutes for light to leave the Sun and be reached at the Earth. And you can see these distances increasing here. Mars takes nearly 13 minutes. Jupiter, 44. By the time you get to Saturn, you're talking about hours here. So light leaves the Sun. It takes nearly 1.4 hours for light to reach Saturn. Uranus is now at 3, Neptune at 4, and it takes nearly 6 hours for light to reach Pluto. The planets are also varying sizes and various densities. And if you're looking at their gravities, you actually have a variety of different surface gravities. We'll talk about gravity in a little more detail later on, but you can see that the larger the planet, the greater its gravitational pull. Planets such as Mercury and Venus are relatively small, so their gravity here given is a fraction of Earth's. 1g here on Earth, 1g is our surface gravity, that's equal to 9.8 meters per second. Venus, very close to the Earth, about 95% gravity. Mercury, 0.39, Mars, 0.53. People often forget Mars is a very small body. Jupiter, about 11 times Earth gravity. Saturn, about 9. Uranus, Neptune, very similar, around about 4 times Earth gravity. These, of course, are gas giants and do not have a discernible solid surface that you could go and stand on. So these quoted gravities are the gravities at the surface of their atmospheres, at their very outer skin. And then finally Pluto, tiny little Pluto at 0.18. So 0.18 here of Earth's gravity. And the masses here, which correspond to those gravitational pulls, are quoted over here. So, when we're talking about distances, the furthest that people have got is actually by our probes. We have not sent people beyond our solar system. We have not sent people beyond the moon. The moon is the furthest that humans have actually traveled, but we have sent mechanical probes further out into space. The furthest of these are the Pioneer and Voyager probes. Voyager 2 here that we'll talk about was launched in 1977, and Voyager 1 also in 77 in August and September respectively. Yes, Voyager 1 was actually launched after Voyager 2. Voyager 1 is actually traveling faster and is now considered the most distant human object since 1998. So it actually passed one of the Pioneer probes and is about 19 times 10 to the 9 kilometers away. Voyager 2 is not far behind it at about 16 billion kilometers. These numbers are a little older now since I composed these slides, and if you actually want to see the true distances of these probes, please go to this link and you actually see an update second by second telling you how fast these probes are going and their up-to-date distances in a second by second basis. These probes are still actually communicating with us and are telling us a lot about the edge of the solar system. Occasionally you will see a news story where they encounter, say, an energy flux, where they actually pass through a barrier of energy towards the edge of the solar system and measure it using these magnetometer booms and their various cosmic ray instruments. The cameras, unfortunately, on these spacecraft have long ceased to function. But the Voyager spacecraft were launched to explore our solar system. So Voyager 1 is here seen at Jupiter in March 1979. As it passed Jupiter, it picked up a lot of energy and as such increased its speed enormously. Voyager 2 here went to Saturn and actually passed through its rings. And then both spacecraft went on to the outer solar system. Voyager 2 took advantage of an actual conjunction of the planets, of the positions of the planets, and could actually go by Uranus, discovering its rings or confirming that its rings existed. And then past Neptune. So Voyager 2 did what was referred to as the Grand Tour. It passed fairly close by Jupiter and imaged that, and then it went by Saturn, Uranus, and Neptune and told us a whole wealth of information about the edge of the solar system. Voyager 1 was really a Jupiter flyby where it picked up a lot of energy and then sped out to the outer solar system. So these spacecraft are moving extremely fast, and their mission is really continuing as they go out into interstellar space. Interstellar space being that space between the stars. So that was the solar system, the sizes that we can see in the solar system, the size scales, and the kind of units you would expect to see within the solar system. We now want to look at the kind of distances between individual stars. So the solar system was the planets and the asteroids and everything else all rotating around the sun. Now we want to look at the proximity of the sun in relation to other stars. Now, as we saw from our previous table, the distance from the sun here to the Earth was about 8.32 light minutes, or 1.9 times 10 to the minus 6 light years. The distance from the Sun to one of the nearest stars, Proxima Centauri, is 4.2 light years. Distance to Rigel Centaurus, 4.3, Barnard star, 6, Wolf 359, 7, and Sirius A and B, a double star system, hence the A and the B, being about the same distance here of 8.6 light years. For comparison, the light travel time from the Earth to the Moon is about 1.3 seconds. So the Apollo astronauts, when they stood on the surface of the Moon, would say something, and then it would take about 1.3 seconds for that signal to be transmitted to the Earth by radio waves. So that's just for comparison. But these are the distances to the nearest stars. If you were traveling at the speed of light, it would take you between 4 and 8 years to reach the nearest stars. So when we're talking about stellar distances, we can define these distances to the various stars from the Sun. So here's the Sun over here. Here's Centauri A, Centauri B, and Proxima Centauri. If we're looking at these distances, you can see the distance to the Centauri system is more zeros than I'm willing to attempt to count in kilometers. If we translate this distance into astronomical units, it's a little more manageable at 275,093 astronomical units, but still doesn't really roll off the tongue and is not great to quote to an audience. So if we go for the light year now, it becomes the much more manageable number of 4.35 light years. If we do the same thing for Proxima Centauri now, which is a much smaller star, these are vaguely to scale, and these two stars here, and we'll discuss this later, are different colours. Centauri A is white, Centauri B is a lot redder. And we'll talk about why those things occur. But back to units, here's Proxima Centauri, and you can see here's our zeros again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 kilometers, or 271,000 astronomical units, or the more manageable 4.22 light years. So Proxima Centauri, a little bit closer than the Centauri A and Centauri B system. Centauri really meaning that these stars are all in the Centaurus cluster, the constellation, I apologize. So those are the kind of things you should expect to see in terms of stellar distances. These are way bigger than a solar system. So we just stepped up to the next distance scale when we start talking about the distances from a star to another star. And here's the local neighborhood for our star, for the sun. In a radius of about 10 light years, so a diameter here of 20 light years for this circle. In that 20 light years, we have all of these various stars. And one of the things to note is these stars are not all just a straight line from the sun. Some of them are higher than the sun, some of them are lower than the sun. So these distances are a little more complicated than just driving in a nice straight line to each one of these, and at all sorts of different heights in the galaxy. In the nearest 20 light years to our star, we have about 83 star systems. And that means 109 stars or brown dwarfs are located in these star systems. This is not wrong. There are more stars than there are star systems. So there are 83 solar systems like our own, with a star with planets and debris going around that star, and there's 109 stars in the local universe. That means there's more than one star in most solar systems. And this is one of the things we start to see when we look around the universe. Stepping up a little more, we just looked at the distances between the stars. Now we can look at the distances through our galaxy. So here is the center of our galaxy, and what you can see here are arms comprised of stars, dust, and gas. Where you see these red patches and where you see the points of silvery light, this is probably star formation and dust that's being reflected. Where you see the black, darker material, this is light that's actually being absorbed by the material in the galaxy. So here's the very luminous center of our galaxy, and here's us. Here's our star, a fair distance out here from the center of the galaxy. Inside our galaxy, there's about 200 billion stars. That's a lot of stars. And that's just in one galaxy. And as we'll see later, there's many, many galaxies. Our galaxy is about 100,000 light years in radius. So 200,000 light years all the way across. And our star, the sun, and us going around it are about 26,000 light years, or 26 times 10 to the 3 light years from the center of the galaxy. Now the center of the galaxy is very luminous. It's throwing out a lot of radiation, both visible and invisible, and you don't want to be too close to the center of that galaxy. So when we are looking for planets that may have life on them, there will be a minimum distance from the center of the galaxy that we'll have to look before they get irradiated. Too close to this center, too much radiation. But anyway, returning to distance scales, that's our galaxy. That's its distance, its radius, hundreds of thousands of light years, and that's what you really need to take home, is not memorize these numbers, but have an idea. Hundreds of thousands of light years is sort of the radius of the galaxy. Tens of thousands, 20,000 light years or so, is the distance from the center of the galaxy to the sun. So what's the size of a solar system? What's the size of a galaxy? In sort of broad terms, you do not need to memorize these values so much as saying, well, it's hundreds of thousands of light years for the dimensions of our galaxy. If we look at our galaxy from the side, it's a spiral, but it's an extremely flat spiral. So here's that center of the galaxy that we were talking about before, and it's actually a bulge. It's almost a sphere sitting at the center of our galaxy, and then all the other stars are sitting around in this disk and are orbiting the center of the galaxy in a flat disk. There's a few stars above and below, but this distance here, the actual thickness of the galaxy overall, is about 114 light years from the top to the bottom here. So that's the scale we're looking at. 27,000 light years here from the star, our sun, to the center of the galaxy, and about 114 light years in thickness. So the galaxy is a lot thinner when you look at it from the side than it is wide. So when we're looking at the size of our galaxy, we're looking at vaguely 100,000 light years. There are different sizes of galaxy. Not all galaxies are this size. Some are bigger, some are smaller. There's a whole different array of sizes of galaxy. Larger ones, smaller ones, different shapes, different morphologies. Excuse me. And we will discuss those later. The Milky Way, our galaxy, also has several satellite galaxies, other galaxies which are orbiting around itself. Some nearby galaxies, when we start looking at the distances to these, the Virgo stream is actually very close. Here's our galaxy at about 100,000 light years across. The Virgo stream of galaxies is only about 3,000 light years away. The Leo 2 dwarf galaxy, now we're looking at about 600,000 to 700,000 light years away. And then a spectacular night sky object that you can actually see sometimes in the right conditions without a telescope or binoculars is the Andromeda galaxy. And that is about 2010 times 10 to the 3 light years, or 2010 kilo light years. So we've talked about galaxies, and we've talked about the size of galaxies. But our galaxy is part of a group of galaxies, and that's referred to as a cluster. And the Milky Way is part of a galaxy cluster which is made up of about 30 or 40 other galaxies. And that's often referred to as the local group. And it's about 1 megaparsec in size, so it's about 3.26 times 10 to the 6, so that's 3.26 million light years across. So this is very big compared to, say, the size of the solar system especially, or even the size of our galaxy. On top of this, you can have groups of galaxies, which are referred to as superclusters. So this is a cluster of galaxy clusters. So first of all, let's define that local group. Here's our Milky Way galaxy right here, with the Sagittarius dwarf galaxy nearby, and various other galaxies. If you go to Australia or go anywhere in the southern hemisphere, you'll see what's referred to as the SMC and the LMC, the large and small Magellanic Clouds. These are nearby galaxies. There are no particularly spectacular galaxies outside of something like Andromeda in the northern hemisphere, but these are very easily visible if you are in the south. So here's our Milky Way galaxy, and here's its cluster of friends, here's its local group. And the local galactic group within 1 megaparsec here has all of these other galaxies. Here's the Andromeda galaxy and its companions. These NGC 185, NGC 147, M110. Andromeda Galaxy itself has a designation of M31. We'll discuss these catalogue numbers later, but there are about 2 or 3 common catalogues of galaxies. There are far too many galaxies to name them all, such as Andromeda having a special name or Sagittarius. So we often use catalogue numbers to discuss these. These are IC numbers, NGC, or the Messier catalogue. And we'll talk a little bit about that catalogue, especially later on. M is for Messier. So anyway, this is our local galactic group. And this, you should remember, is about the megaparsec scale, about 1 million parsecs. And a parsec, of course, is roughly comparable to a light year in scale. So there's our local family of galaxies. Here's that same diagram, just a little less florid. So here's our Milky Way with its various galaxies, and here, of course, is Andromeda. This is presented flipped, just to a bit of a simpler diagram with without so much of the busyness going on. So that's our local galactic group. And of course, our local galactic group is part of a cluster, which is part of an even bigger cluster called a supercluster. And this is our cluster of clusters of galaxies. And the Virgo supercluster that we can see from the Earth here is a cluster of galaxies, and there's about 2,000 individual galaxies. Remember, there were billions of stars just in one galaxy, and here we're looking at thousands of galaxies. The Virgo supercluster now, if we're looking at sizes, is about 200 million light years across. So we're stepping up and up and up in terms of our distance scales. So let's take a look at this. Here we're looking at the universe. And this is the kind of pattern that you can actually see when you look at the universe on a very, very large scale. Gravity organizes itself, and we end up with this kind of mottled, textured pattern to all of the galaxies and all of the material in the universe. And here we're looking at a scale of about 10 billion light years across, or 10 to the 26, 10 with 26 zeros after it, meters. And now we're going to zoom in. If we zoom in, we're now at 10 to the 25. Here, remember, we're at 10 billion light years away. Now we're on the scale of 1 billion light years, or 10 to the 25 meters. Here's our local supercluster. This is a cluster of clusters of galaxies. Zoom in a bit more. Now we're on the hundreds of millions of light years scale, or 10 to the 24 meters. There's our local group. Zooming in a bit more, now we're in the tens of millions of light years scale, 10 to the 23 meters. Again, get an idea of these scales. You don't need to memorize and reproduce these in an exam or assignment anywhere. Just have an idea of what these values vaguely should be. But here we are at 10 million light years. Here's the Milky Way, our galaxy, and here's the Andromeda and its friends over here, about 3 million light years away. So from here, on this side of the frame, to this side, is about 10 million light years. Zooming in a bit more, we're now looking at the Milky Way and its friends, the large and small Magellanic Clouds and the Sagittarius dwarf galaxy, on a scale of about 1 million light years now. Zoom in a bit more. Now we're looking at our galaxy very close up. Now we're on the scale of hundreds of thousands of light years. Zoom in some more. Now we're inside one of the galactic arms of our galaxy. And here's our sun. Now we're on the scale of tens of thousands of light years. Zoom in some more. On a scale of about 1,000 light years, here's the sun. Here's Betelgeuse, a red star in Orion, spelled wrong here. This is actually an S. And here's Polaris. But here's our local stars in about 1,000 light year radius. Zoom in some more. On the scale of hundreds of light years, here's our star the Sun, nearby stars Sirius and Vega. So now we're definitely on the interstellar scale. Zoom in some more. Here's the Sun, about 4 light years away. Here's the Alpha Centauri star. Zoom in more, and now we're starting to see sort of 1 light year scale a solar system forming. So here's the Sun as a dot from about 1 light year away. Zooming in. Now we're starting to transition from light years down to astronomical units. So back here we were at about 1 light year. We're now down to about 7,000 astronomical units, or 10 to the 15 meters. And the Sun is actually now scientifically referred to as a blob. Zoom in some more, and we start to resolve the orbits of the planets. If you had a big enough telescope from 700 AU, you could start to see the planets here. Here's the Sun, Pluto's orbit, Neptune's orbit. Very big scales. Now we're essentially entering the solar system on about the tens of astronomical units, 70 AU scale here, 10 to the 13 meters from here to here. Zoom in some more, and now we're looking at the terrestrial or rocky planet orbits here. Here's the orbit of our own planet, the Earth, Mars, Mercury, and Venus. Zoom in some more, and here's the Earth, and there's the Moon orbiting the Earth. Now we're at about the 0.7 astronomical units, or 10 to the 11 meters. Once you start getting lower than about 1 astronomical unit, it's probably time to start talking in terms of kilometers. So now we're at about 10 million kilometers, and the Moon's orbit starts to be resolved. Zoom in more. Here's the Earth, here's the Moon. Now we're at about 1 million kilometers. Less than 1 million kilometers, 100,000 kilometers, and we start to see our planet. Talking about planetary scale and orbital scale. Zooming in further, when we're at 10,000 kilometers now, we're starting to talk about the size of continents and islands. 1,000 of kilometers scale, we're looking at, again, kilometers, islands, and maybe even city sizes. Hundreds of kilometers, we're looking at local scales, cities, towns. Then we're looking at neighborhood scale at about 10 kilometers. 1 kilometer, you're starting to deal with your local area. And then zooming in even further, at about 100 meters, you're starting to talk about your immediate vicinity. Sort of football field sizes. And then down at the 10 to 1 meter scale, you're talking about your immediate personal space, of which we should always maintain at least 2 meters. So it's nice to see these football players actually practicing social distancing. If we go to the large scale now, and we look at the entirety of the universe, our known universe is about 92.94 times 10 to the 9 light years across. And that's when we start to see that textured or fabric sort of pattern of all of the galaxies in the universe. This means when we look as far out as we can to the edge of the universe, we're looking back about 14 billion years. It takes 14 or 13.7 times 10 to the 9 years for radiation to travel from the edge of our universe to the Earth. And that's in the form of microwaves, or the cosmic microwave background, or CMB. And that travels from the edge of the universe to us. And that's as far as we can see. This is the edge of what we call our observable universe. There is no light beyond that. And our universe contains about 80 times 10 to the 9 galaxies. And each galaxy contains thousands, millions of stars. That means there's about 5 times 10 to the 22 stars in our universe. So 80 billion galaxies and 10 to the 22 stars in the entire universe. That's a lot of stars. And this is as far as we can see. This is the results of what's referred to as the Wilkinson Microwave Anisotropy Probe, which doesn't really roll off the tongue, so it's called WMAP. And these are the microwaves from the very edge of our galaxy. And you can see there are hot spots in places and cold spots in others. And what we're actually seeing here is features from the very beginning of the universe, blown up and smeared across the universe, smeared across the sky. So imagine taking a balloon and drawing a face on it when it's deflated, and then inflating that balloon. Essentially, you drew a very small face on that balloon, but once you've inflated it, you had a very big face. You made its features bigger just by making its medium bigger. And that's essentially what's happened here with the universe. All of these were probably atomic or quantum variations in the early universe. And then as the universe spread out, they became bigger and bigger and more spaced out. So that's our universe. That's our solar system. That's our galaxy and our clusters of galaxies, quantified and looked at in terms of the units that we will use throughout this course, in terms of their distances, in terms of their size scales. And like I said, memorizing all of these values to the nearest decimal place isn't particularly helpful. But knowing what size scale we're dealing with, are we talking about the distances between the galaxies, the size of the universe, or the distance between planets, or even what's the distance on a single planet? Make sure you know vaguely which units you should be using and what those sizes should be.